Hey everyone, Big Mike here. I thought I would just do a bit of a Q&A from you guys. I'm making some slides for my middle school classes math club this week, and I just thought I would, show you guys what I've been doing in terms of math stuff. I know I don't do a whole lot of math videos lately, but I just wanted to show you guys some kind of things that we have been talking about, as well as, just to give an idea, maybe some feedback from you guys if you guys have any feedback about what we could talk about this week. So, normally I start off with a couple of competition style questions because we are going to be going off to a competition sometime during the next semester, so probably around February or March time. Again, our club is not very formal, we're not very rigorous. Basically, we're just trying to, explore these new ideas of students. These students are generally advanced in their grade level. There's some 7th graders who are taking first year algebra, and a couple of 8th graders who are also taking high school geometry. So these students do, they feel like they're advanced. I've seen some of their skills, and they do have some good skills. But of course, we would like to try and improve those skills, of course. But anyway, so enough ranting. Here are some of the kinds of questions that I've been making up for the math club. And if you guys have any comments, questions, normally what I do is I give them an idea of how long they're supposed to take for it. For example, this one should take maybe 45 seconds. I'll give them a minute. That way they can just jot down on some, either pen and paper, or if they have like a dry erase marker board, they can use that totally if they want to. But anyway, so we ask different questions, like suppose the operation x% sine y means to compute the following: xy minus x plus y. So basically the product minus the mean, or minus the sum of the two numbers. So, based on this information, what is 0% sine minus 4, and then that whole thing percent sine, in parentheses, 3% sine 7. Likewise, here's another one that, admittedly, some people, if they know various tricks and stuff, they could get in 3 seconds. Probably less than that. If x has to be greater than 0, solve the following for x. Here's an example of a first round. I changed the names of some of the things to avoid any kind of copyright. As far as I know, these are questions that I made up and are not owned by that company at all. So here's the question that I made up that would qualify as perchance a first round type question. How many 3-digit numbers are there such that the sum of the 3 digits is exactly 9? And then lastly, actually I usually try to make the last question kind of a follow-in to the lecture, topic that I make for the day. So, find the area of the following triangle, given that it has these side lengths. That's all the information that is given. So, talking about triangles, you may realize that this is in fact a right triangle, but perhaps students don't see that as right away. So, I thought I would talk about the Pythagorean Theorem, and then, time permitting, maybe go into Heron's theorem as well. Mostly these are pictures that I drew. A couple of them I did pull off the internet just from a random image search. So if, as far as I'm hoping that these pictures are not, copyrighted or anything, but, well, I'll get to those when I get to those, I suppose. So the Pythagorean Theorem is one of the most common formulas talked about in middle school or perhaps early high school. Basically what it does is it relates the sides of a right triangle. So, of course, triangles have 3 sides, and a right triangle will have a 90-degree angle, usually indicated by the little square at this point. So, of course, one notices that the 2 sides are perpendicular to each other as well, creating that 90-degree angle. So, if we let C be the longest side of this triangle, we often call it the hypotenuse, and let A and B be the other 2 sides, it turns out that for a right triangle, there was this relationship that A squared plus B squared is equal to C squared. So again, where A, B, and C are the lengths of the sides of the triangle. So of course, solving for C by itself, we have the positive square root of A squared plus B squared. Of course, hypotenuse is kind of hard to spell sometimes. So why does this work? Again, there are some students who are in high school geometry classes, but they haven't gone to, similar triangles or any rigorous algebraic proofs like that, or geometric or algebraic proofs. So I just figured for everybody, I would just show this general picture from Wikipedia where basically if you have A, B, and C as your sides of your triangle, then you can form a square on the side for A that has an area of A squared, a square for B that has an area of B squared, and in fact you can combine these two into a square such that the area down here is C squared. So again, A squared plus B squared equals C squared. There are some common Pythagorean triples, as they're usually called. Basically sides of integers that make nice Pythagorean, that apply to the Pythagorean theorem very nicely. So of course 3, 4, 5 is a very common one, and I just mean like one has a side of 3, one has a side of 4, one has a side of 5, not 3 minus 4 minus 5 or March 4th, 2005, anything like that. Of course, there are an infinite number of triangles that work like in this situation, but of course there are plenty others that have decimals and irrational numbers as well. So just as a super basic example, so that all students, again, not all students have dealt with solving for quadratics at this point, but I figured that this would be a straightforward example for the students to work on, maybe take them at most a minute. Well, it'll take some a minute, it'll take some probably a little bit longer until they copy off of their friend. But again, this is a very informal club, just very, it's just more inquiry, just to get ideas in the students' heads as well. So of course, it's like here, find the third side of a Pythagorean triangle, or of a right triangle. So of course, basically, just plugging in the numbers and solving for A tells us that it has to have a length of 6. So at this point, I emphasize the fact that 6, 8, and 10, well, that's just exactly the same as doubling the 3, 4, 5 triangle. So if you just double the length on each side, in fact, you are still going to have a Pythagorean, or, an awesome right triangle. So in fact, if you multiply it by 3, by 4, by 1/2, by 1/10, it still works, as long as you multiply that same number to all sides. So, of course, the question is, we know that if it's a right triangle, then we have this Pythagorean relationship, but in fact, the converse is true. And admittedly, not all students are familiar with the word converse, so I just thought I would mention, rename the statement here so that it does follow the definition. So if a triangle has length and this property, then in fact the converse is true and it is a right triangle. So this is an if and only if situation. I decided to put in one basic application of the Pythagorean theorem that students have seen before, and yet they do not connect the two things together. So the distance formula, basically between any 2 points on a coordinate plane, can be described by this formula here. But note that this is exactly like c equals the square root of a squared plus b squared, where indeed you can just either count squares or by whatever the scale is on your particular graph. And in fact, you can just use the Pythagorean theorem in that situation. And of course, we have a right triangle right here with our 90-degree angle. So I thought I would have one extra practice problem just to see how quickly some of these particular ideas were popping in. Again, some of them have seen the Pythagorean theorem before, but then that was it. They just used it without a whole lot of basis about what it is or where it comes from or anything like that. So here's just a quick practice of them. Hopefully that they'll be able to find the lengths of these 3 segments pretty straightforwardly. I then decided to go into a little bit of a side story. So if I don't have time permitting for this thing, I will skip it entirely. But of course, there are different triangles besides just right triangles. So again, for those who have not had the formal geometry vocabulary, I mentioned the definitions for acute triangles and obtuse triangles, as well as emphasizing that in fact the sums of your interior angles of a triangle do have to add up to 180 degrees for these planar triangles. That's all we're just doing, are triangles in 2 dimensions. I then bring up the inequalities that students can actually use to determine if a triangle is an obtuse triangle, a right triangle, or an acute triangle. Of course, if it were the case that a squared plus b squared equals c squared, then we know that it's going to be a right triangle. Of course, where do these inequalities come from? Basically, they come from trigonometry and the law of cosines, if you guys remember those particular equations. But since these students have not seen trigonometry in the least, I'm just going to leave it as inequalities at this point. And again, they can play around with these particular side lengths and determine whether or not certain triangles would classify as acute triangles, right triangles, or obtuse triangles. I'm also giving one example of a none of the above, because they also should be aware of a triangle inequality issue. I mean, think about it. If you have a side length 4 and a side length 6, there's no way that's going to, match it back up to a triangle with side of length 12. It's going to look like two stubby arms that can't meet up to each other. Something like that. So indeed, some students have probably seen or heard of the triangle inequality theorem. I'm not sure if that's mentioned in the geometry courses or not. But I think it would be useful just to kind of, mention it briefly without going into a whole lot of detail about it, just so that, students might be aware of these things instead of just trying to plug in numbers, because that's usually what I see happening too often. Students get a formula, they just plug in the numbers without really thinking of the context of where these things are coming from. So my last section that I decided to talk about is a notion about the area of a triangle. And again, for this whole lecture, I have about an hour's time, more or less, a little less than an hour. So, of course, I'll have plenty of time for the students to work on stuff, to talk with each other, to have snacks, stuff like that. It is an after-school club. But last section I wanted to discuss was the notion of area of a triangle. So most of them hopefully know that formula 1/2 base times height, or base times height over 2. And again, even if it's not a right triangle, we can talk about finding the base and the height for different kinds of triangles, as I drew here in the picture. And I forgot the little right angle here to emphasize that this side h is essentially the altitude of the triangle. Again, I'm not focusing too much on terminology, but just to emphasize that that's how high the triangle goes. So at this point, I just wanted to introduce the notion of the hero's formula, or Heron's formula, or Heron's theorem, however you may be familiar with it. Basically, where we can determine the area of a triangle even if all we know are just the side lengths. So I gave them the formula on this particular page, where I try to emphasize that, I had mentioned before for right triangles that C was supposed to be the hypotenuse, the length of the longest side, but in this case it doesn't really matter anymore, because we're just, trying to basically plug these into a formula, and these students do not have the algebra skills for me to explain where this formula comes from at all. So I'm not going to be concerned about that. So what I decided to do was show them a trivial, well, not a trivial example, but a proof that this weird convoluted formula actually does work, even in the situation of a nice right triangle, where we can compute the area of it just really quickly. So for a 3, 4, 5 right triangle, we know 3 and 4 are the base and height, so half of 3 times 4, well, that's 6, duh. So I also tried to emphasize plugging it into the formula, and then going from there. So plugging all of our values in, etc., and computing. Admittedly, some of these students are still in algebra. Some of these students have not had proper work with radicals and exponents. So I figured it'd be worthwhile just to do a quick topic about the different kinds of things that they can see here. So, for example, that the square root of product is the product of the square roots. Again, assuming all of our numbers are positive, we work in real number land in this, for this grade level, for these, for the school level. So I did want to emphasize also the idea of simplifying your rational expressions. So, for example, the square root of 45 on an example during the competition or something, that would not be an acceptable answer. So you have to pull out any squared factors of that particular number, and then you can simplify it to something nicer. I thought I would end off with just a quick example. Again, some students have to take the bus, some students can stay a little bit longer, some students have sports after school, even after the club. So, for those who can stay around, just kind of a end challenge or end question, kind of bring a little bit of closure just to talk about. We talked about areas of triangles, we talked about perimeters of triangles, we talked about properties of triangles. If I had time, I might ask the students if they knew that this was a obtuse or acute triangle or a right triangle. What are some different ways that we could test for this as well? So this is just a idea of some of the stuff that I do for the middle school math club. Again, I think I've kept all the pictures and possibly copyrighted phrases taken care of. But these are the kind of things that I hope maybe I could... if you guys would like me to go through this as a formal discussion. I've done a couple of topics like this, so I've done, some things on combinatorics, I've done some things on polyhedrons, or polyhedra, so, just various topics that the students don't normally see in their regular algebra or geometry lectures. Or, again, the club is open to all students, but it's mostly the advanced students that have been coming to this club. So let me know if you guys have any recommendations or ideas for this, or if you have ideas that I could use maybe for other weeks of things, or just, do I have too much time? And basically any critique that you have would be appreciated. Okay, this is Big Mac saying, later.